All right, I think that you should be able to see my screen. Okay, so so today I'm going to talk about. All right, perfect. I know there's obviously everybody is working on deep learning, but I'm going to do something a bit different. I'm going to talk about something which is pure audio signal processing this time. So this is a project that, so when Masahito asked me to come and present something, I was trying to look for a project I could talk about, because lately at GraceNote, what I'm doing is either I cannot talk about it or it's not something that interesting to talk about, but this is, I think, a project that could be interesting that I worked on like a couple of years ago. And I'm going to explain what sliding DFT is and what is kernel windowing. So, okay, so just a little introduction. I would just want to introduce myself again. So I'm French, but since Utah is translating me, I don't know if everybody can hear the accent. Thank you, Utah, again for being my interpreter. My first time as like a kind of doing research, I was actually a research engineer at Audionamics in France, where I was working on audio source separation. Then I did my PhD in electrical engineering and computer science at Northwestern University, where I worked in a lab called Interactive Audio Lab with Professor Brian Pardo. In that lab, I worked on pretty much a lot of like audio related projects. And my thesis was actually also about source separation, but this time using repetition, something completely blind, unsupervised, no deep learning involved here. And then I became a research engineer at GraceNote, where I basically worked on everything audio related. And this is actually where I met with Masahito. So some examples, for example, I worked on cover song identification or live song identification, on audio fingerprinting. So this is things like, for example, Shazam, if you heard of that. On audio encoding analysis, this is basically to analyze an audio recording and try to detect which type of coding format was used, compression algorithm was used, for example, MP3, AAC, whatever, to encode this audio. And actually, the project, the topic I'm going to talk about today is related to that. I will explain this. I worked also on beamforming, classification, and many other things. Right, and also as Masahito said, I'm also the co-organizer of the San Francisco BISH Bash, and we have now. I'm very happy that the Tokyo BISH Bash are happening. We also have the Paris BISH Bash, and there's also one in London now. Okay, so briefly, I'll show you my plan. So this is going to be a lot of math, no audio examples. So I apologize if the presentation is a bit dry, but I will try to make it as clear as possible. So the first thing I'm going to do is to talk about what is the sliding DFT. Before I talk about the sliding DFT, I'm going to remind you what a DFT is, a discrete Fourier transform. Then I'll show you how to derive a sliding DFT and what it is. Then I explain what are the limitations of the SDFT, which is actually you don't have windowing incorporated in the algorithm. Then I'll explain what is the thing that I propose to basically incorporate windowing into that algorithm, which is called kernel windowing. I'm going to remind you what Parseval's theorem is. So I told you it's going to be very signal processing, audio signal processing. And we're going to use that to basically derive SDFT, but with a windowing incorporated in it. And I'll show you that incorporation, that extra computation will still keep the algorithm computationally efficient. Then I mentioned one application in particular, which was audio encoding analysis, in particular framing detection. I will explain what it is. Then I will explain how to derive something called sliding modified discrete cosine transform with a windowing included in it. This is something, a transform that's typically used when you do audio encoding. Just a bit of extra analysis to explain what happened actually, the errors we get. I'm going to explain that, and what computational complexity we have when we add the windowing. And I'll show you basically the whole algorithm stays computationally efficient. Okay, so a reminder, discrete Fourier transform. I'm hoping that everybody here knows what the DFT is. The DFT is basically the discrete Fourier transform, where you trying to transform a time domain signal into a frequency domain signal. So this is the equation here, and I hope everybody knows it. This is very important. So the big X here represents the DFT at the frequency index K, and the small x would be the signal here. All right, so let's move on. This was easy. Now I'm going to talk about the sliding discrete Fourier transform. So what is the SDFT? So the SDFT is basically an algorithm that that helps you compute the N-point DFT of a signal that starts at a sample using the N-point DFT of the same signal but starting at the previous sample. So essentially, it's a recursive algorithm. Let's say you want to be able to compute the DFT of a signal at and your hop size basically is one sample. Instead of having to compute your SDFT from scratch every time, there's a technique to basically use some sort of recursivity, which will help the algorithm to be very efficient. And this is the equation of the SDFT. Very simple. Again, remember the big X's represent the DFTs, and the small x are the signal. So when I wrote big X with the I between parentheses here, I mean that it's the N-point DFT of the signal X starting at I. So it goes from I to N. From I to I plus N, actually. And yeah, so we're going to use the previous DFT, the DFT of the signal starting at I minus 1. And we're going to just remove the value of the signal at I minus 1 and add the value of the signal at I plus N minus 1. And there's going to be a phase element also that we're going to need to multiply. So this is the very simple equation of the SDFT. With this, you can have, if we have already the DFT of the signal just before, and you move just from one sample, you don't need to recompute everything. You can just use this simple algorithm for that. So I'm just going to here show you how to derive this. It's pretty straightforward. Like the thing that you need to know is that the SDFT basically relies on the shift theorem, which basically says that the DFT of a shifted signal equals the DFT of the original signal multiplied by a phase, the same phase component that I showed you before. So this is again the DFT of your signal starting at I. Then what we're going to do, we're just going to extract like a phase component out of the definition. Then we're going to reorganize the indices. Then we're going to try to extract basically like the DFT of X, but starting at I minus 1. Okay, that's maybe I'm going a bit fast, but trust me on the math. And then yeah, like that's it. Basically, like when you reorganize the indices, extract that DFT of the X starting at the previous sample, you get the definition of the SDFT. So pretty straightforward. But here's the problem. The problem is that although it's an efficient algorithm, it doesn't allow the use of a window function incorporated typically in the computation of a DFT. Because if you incorporate a window in the SDFT, it will break the sliding property. So this, what I'm going to show you here, is basically the DFT of a window signal. So now we have like a window function included in the definition of the DFT. But now, if we try to do use the algorithm to compute the SDFT, that XW, like the W here means that it's the DFT with a window in it. The equality will not hold. So we have a problem here because there are many cases where we're going to need windowing. So how are we going to deal with this? So before I explain how to deal with this, I'm going to remind you what Parseval's theorem says. So Parseval's theorem, basically, this is Parseval's theorem. It basically says that the dot product between two time domain sequences is equal to the dot product of their time frequency, of the frequency domain transform, sorry. Basically, this just shows the energy conservation between the time domain and the frequency domain. So you have two sequences, sequence 1, and the complex conjugate of sequence 2. And the DFT of sequence 1, complex conjugate of DFT of sequence 2. This is what the Parseval's theorem is. And this is something you should know also, very important. All right, now I'm going to show you how basically derive an SDFT, but that will include windowing in it. What we're going to do is we're going to use Parseval's theorem to translate basically the DFT of a window signal into the DFT of the signal without the window, but we're going to extract the windowing outside of the DFT basically. So we're going to do the windowing after we compute the DFT. And to do that, we're going to basically extract some sort of kernel, a kernel that is derived from the window function. So let me show you how to derive this. So what I'm showing you here is the DFT of X, but with a window this time. Okay, DFT of window of X starting at I. Now we're going to use Parseval's theorem to get basically the DFT without any windowing, the big X here, and a kernel that will incorporate the window and some other terms also. And then that's easy then. Like now we have X, we can replace X by using the sliding DFT transform algorithm, I mean. Now that we have the definition of, now we have the DFT of X without windowing, we can now reuse the previous, DFT of the sample starting at I-1. The only thing we have to do is basically, once we apply the SDFT, multiply the result by kernel. So the sliding property remains, but every time the new DFT is computed, we need to apply that kernel. So that's what I call SDFT with kernel windowing. But here's the thing you're wondering. Now we're going to have an extra computation here. So first thing you need to know is that that kernel is completely independent of the signal. It only depends on the window function. That means it only needs to be computed once before the whole SDFT process. In fact, if I show you what that kernel is, so if I develop that equation, so let's replace the y by what y is, which include the window function, and then you get the final DFT of the kernel. This is how it looks like. So it's a very simple equation. But now, okay, now you can wonder, all right, this is probably heavy. You need to multiply that by the whole to the SDFT. This is like something which is n by n. If n is 2048 by if n is 2048, the kernel would be 2048 by 2048. That's a lot of computation. But here's the cool thing is that this type of kernel typically would be very sparse. Either it will have a lot of zeros, or it will have a lot of values that are have very low energy. So only few values in that kernel will be actually meaningful. So what we can do is actually zero all the values below threshold and get a very sparse kernel. And if we have a sparse kernel, that means less computation. In fact, I'll show you some example. If you compute that kernel from a Hanning window or Blackman window, what I'm showing here actually is like it's the first 100 coefficients on the 2048 by 2048 kernel. So I'm showing you just the 10 by 10 at the lower left corner. So if you compute that kernel using from a Hanning window, you get only basically 3 diagonals. That means there are only 3 computation that you're going to do, extra computation that's going to be added to the SDFT. For the Blackman, you get 5 values. Everything else is 0. Now we can have some other windows, for example, the triangular window, or the Parseval window, or the Gaussian window, or the Kaiser window, where it's not 0 everywhere. You do get a lot of values. However, those values are mostly very small. Since they're small, means they're not significant. We can zero them using some threshold. And I'll show you in the end that zeroing those values and using that kernel, that sparse kernel that we obtain from it, will basically not change the result that much. Okay, I hope I'm not going too fast. This is a lot of technical details, but now let me just show you an application so you can have an idea of what's the point of all of this. So, so this is, I'm going to put this, so the application is framing detection, and I'm going to put this into the context of audio encoding analysis. So as I said, audio encoding analysis is a technique to basically, from an audio recording, if you don't know what coding format was used to encode that audio, it's to analyze the audio and basically try to find traces of compression to try to link that to the type of coding format that was used. Because low-sync coding format like MP3, BISH, AC3, when you're gonna use that those formats to compress your audio, you're gonna remove some information. So it's gonna leave traces of compression that us humans cannot hear, but they can still be detected in the audio. And they will be very like depending on the so if you basically reuse the same parameters that were used during the encoding, and if you align them exactly on the sample where those when the Fourier analysis was done at the encoding, you'll be able to actually I need to show you the picture that will make things more clear. You'll be able to find those holes that were removed, that energy that was removed when the coding the compression happened. So the first picture I'm showing you is the time frequency of an audio that went through one of the coding formats. If I don't remember which one, let's say it's MP3 here. What we did, we know what the window function is in MP3. So we use that window function we know the size and we know the type of window. We use that window function at different samples. And if we hit the right sample where the compression happened, we're going to see this exact picture, which is a clear-cut high-frequency cut and clear holes from which energy was removed. Those are things that we don't hear because the algorithm is well made, but we can still detect this. And if you just move one sample left or right, if you do your framing, if your framing is not nicely aligned, you don't get to see those holes as clearly. So again, the point of this audio encoding analysis, that framing is to find the right framing. Where did that Fourier transform happen with which window and which window length? So that's what framing detection is. So you can understand that in this case, we need to basically run Fourier analysis at each sample. That's very computation expensive. We don't want to do that. So we want to have some sort of algorithm like a sliding discrete Fourier transform to basically reuse the previous transform that we computed so that it's efficient. The thing is that typically those coding formats do not use the DFT, sorry. They use something called the MDCT, the modified discrete cosine transform, which is kind of based on the DFT. And as I said, depending on the audio coding format, different window lengths and function would be used. So this is the equation of the MDCT. And as you can see, there's no window in it. Right now, there's no window in it, but we're going to add a window depending on the audio coding format that we're using. So how are we going to be able to compute some sort of sliding MDCT with windowing in it? We want to do that, again, as I said, because we don't want to compute that MDCT at each sample and try to look at the spectrum and see, okay, are there holes here or not? Go to the next sample, recompute the MDCT. We want to be smart. We want to try to derive a sliding MDCT, but we need to include some windowing in it because those different coding formats use different windows. So we're going to derive an MDCT, sliding MDCT with kernel windowing. We're going to use the same thing I did before with the SDFT. So this is the equation of the MDCT, but of a windowed signal this time. I included a window in it. Same, we're going to use Parseval's theorem to basically turn this equation into the DFT of X, just the DFT of X, and a kernel that's going to include that window and also that cosine function that you see there. And then that's very easy. Now we have a DFT of an unwindowed signal. We can use the SDFT easily here, and we multiply by kernel. That's as simple as that. We obtain our sliding MDCT with a kernel windowing. And then, as it was the case with the SDFT, those kernels are going to be independent of the signal, and also they can be made sparse. So I'll show you one example of kernel. This time I'm showing you the whole kernel. In the case of the, this is the kernel for the case of the MP3. As you can see, most of the, this is a 512 by 1024 values. As you can see, most of them are 0. The only values that are not 0 are 2 diagonals. And this is computed from the sine window that's used in MP3 typically. For Vorbis uses another size. You see the size is different here. We have a kernel which is a size of 1024 sorry, by 2048. And it's based on the slope window. I'm not showing the equation here, but those are different type of windows. Again, as you can see, most of the values are zero or very small. That means we can sparsify this kernel. And this is the type of kernel that's used in, the type of window that's used in AC3, which is the Kaiser-Bessel derived window. And the same, if you compute the kernel from it, you get a quite sparse kernel where you just have those 2 diagonals and most of the values are very close to 0. Okay, so I talked about how to sparsify the kernel. Now I'm going to show you that sparsifying the kernel doesn't actually create a big errors actually. So I mentioned the four first windows, the triangular, Parsen, Gaussian, and Kaiser that I mentioned at the beginning. I used the 2048 window of 2048. What I did is basically the error that you see there. I decided to use a threshold. I say everything below 0.01, I will zero it. And basically the error that I'm showing you here is when you compute the energy after thresholding of the whole kernel divided by the energy before thresholding. That will show you how much of the energy is gone, basically. And you can see you get very small values. For the triangular, you get something like 5% of the energy is gone. For something like the Parseval is like 1%. So it's like very, very small energy is gone. And when you remove that energy, you end up with just few values over the diagonal. What we see, what I call the non-zero values. Those diagonals, that means just few extra multiplication or addition. That's it. And for the case of the MDCT, I showed you the sine, the slope, and the KBD window. And you can see that the same when you do, and you can see the window lengths are different. And you can see that when you do the sparsification, you also see that the errors will stay very small. So virtually, after sparsification, you still get the same results. And you get just extra, that K values, you get just few diagonals left on the kernel. So I mentioned that K value because that K value is going to be added, obviously, to the computation, but it's a very small values. So it will not change anything. So I'm showing you some complexity here. You can see the computational complexity of the DFT, the FFT. So the FFT is quite fast, right? It's n log n, but you don't want to do n log n at each sample. That still would be will take forever. Since the SDFT only it's a recursive algorithm that relies on the previous DFT, it's going to be linear. It's going to be an ON. The kernel windowing, you're going to have that K value that's going to be added into the addition and multiplication. But since that K value is small, typically 5, 3, as I showed you before, after sparsification of the kernel, it still keeps everything linear. So that's still fast. Same thing happened with the MDCT. The MDCT itself, you can use the FFT to compute it, would be n log n. Still not efficient if you want to do it every sample. But you can use a sliding version of it that I showed you before that would be linear. And using a kernel will add just that K values, which are quite small, maximum 6 maybe, which will keep everything still linear. Okay. I guess that's it. Those are just some references. And then I just wanted to say Arigato Gozaimasu. This is actually a picture of Masahito when he came to visit me at Grace Note a few years ago when I still had long hair. If you want to find more information about me and also find that paper, that's my website. I also have a GitHub repo if you want to check some of my code that I put online. I have like my own little toolboxes in Python, MATLAB, and even Julia. You have the link to the SF BISH Bash, and we also have a little YouTube channel. So you can look, just type BISH Bash Meetup on YouTube, and you'll find some videos of our San Francisco BISH Bash from that we did before. Thank you.
Hi, Zafar さん、ありがとうございました。
Thank you.
はい。ではですね、質疑応答に入りたいんですけど、ちょっとまだ質問が来てないですね。このセッションの後でも結構ですので、質問がある方はですね、Q&A の方で受け付けておりますので、よろしくお願いいたします。戸上さん、なんか、
私から質問してもよろしいでしょうか。
はい、お願いします。
はい。面白い発表ありがとうございました。ザファーありがとうございます。
Thank you.
で、今、ワンサンプルずつデータをずらしていったと思うんですけど、例えばもうちょっとそれをこう、2サンプルとか、例えば10サンプルごとに、DFT したいっていったときに、そういった場合でも効率的にできるものなのかとか、なんかそういったところをもしなんかご存知でしたら教えてもらえると嬉しいなと思います。
So this was an old project. I'm not working on this anymore, but yes, there are ways to do more than just one sample. There's some sort of compromise, right? If you do, if the jump is too much, then the sliding will not be efficient anymore. You need to redo the FFT. This case, I was interested in just sliding of one sample because for framing detection, that's what I needed. So I'm seeing like a question, an open question. Should I read it?
ありがとうございます。
Okay. Yeah, of course. And I'm seeing some open question. Should I answer them?
はい、そうですね。じゃあ順番に行きましょうか。今、視聴者の方から見てないので、一つずつ、上の、ロビンさんからですね、いただいております。Hi, thank you for the interesting presentation. I'm wondering in practice how much gain you get since log n and 2k may be quite close. こちらから回答いただけますか？log n と 2k は非常に近いので、どのぐらいの利益が得られるのかという質問ですね。
Yeah, okay. So should I read it in English? So it's hi, thanks for the interesting presentation. I am wondering in practice how much gain you get since log n and 2k may be quite close. So not when you have like, so n typically, let's say, if we work with something like an MP3, n would be small, would be like 512, but k in this case is very small, very, very small, like maybe 5. So you have something which is n would be 512, 512, 2k would be 10 maybe. So log n will still be much bigger than 2k. If I don't know if I'm answering the question correctly here, but yeah. There's another question? If I should I read it and
はい、お願いいたします。
So the next question is
そうですね。お願いできますか。では。
Okay. So the next question is MP3 implements a hybrid filter bank where MDCT is applied to an FIR-based filter bank where downsampling applies. Can you tell how to handle this pre-process before MDCT? So that's true. MP3 is a bit more, it's not just MDCT, but it's a bit more complicated, but in practice, just when we were doing the framing analysis, the framing detection, we didn't need to do all exactly everything that was done during encoding. Just doing an MDCT and using the right window size for MP3, which is actually I said the wrong thing. 512 was for SE3. MP3 is a weird window length, is 1,000 and something. But anyway, my point is that we didn't need to do all the other steps that were typically done at encoding. Just using the MDCT with the right window function and the right window length, we were still able to see those traces of compression that were needed for us to say, okay, this is MP3. So I hope I answered that question.
はい、ありがとうございます。筒井さん、回答になってますですかね。はい、ありがとうございます。以上2問いただきましたけど、他に何か皆さんありますでしょうか。大丈夫ですかね。もし追加の質問があったら、Q&A の方にですね、引き続き登録いただければ、後ほどテキストで回答させていただきますので、よろしくお願いいたします。はい。ではですね、ザハさんのセッション以上になります。本当に、今そちらはだいたい24時ぐらいですかね。多分日付が変わったぐらいだと思うんですけども、本当に夜遅くのセッションありがとうございました。
Thank you so much for having me. That was very fun.
はい、ありがとうございました。皆さん、拍手は多分、音としては聞こえないと思うんですけど、心の中で盛大な拍手をお願いいたします。はい。では、ザハさん、ありがとうございました。
Thank you.